From today, we will start the issues of angular momentum, and after that, we'll go into spin. And since in the beginning of the course, when I was asking you about what you are comfortable with, what you would like to learn in this course, some of you said that you would like to hear about the Stern-Gerlach experiment. So while we go into angular momentum, let us go through the Stern-Gerlach experiment. So in the Stern-Gerlach experiment, okay, before we go into the Stern-Gerlach experiment, basically this is related to the measurement of angular. And since we cannot really observe atoms or molecules rotating, the rotation of angular of such microscopic bodies, we cannot directly measure the angular momentum. But there is something that allows us to measure slightly different way. It is that most atoms behave like tiny magnets. So if atoms behave like tiny magnets, then by the way, my microphone is unmuted, right? Yeah. If some atoms behave like tiny magnets, in fact, based on that, you have the whole MRI scan and things like that. There are technological applications of that. But the fact is that many atoms behave like tiny magnets. And in that, we can show that there is a relationship between their magnetic properties and their angular momentum. So in order to see how it comes about, I will rather take you through the classical picture because that is easier to understand. And the quantum picture will be different, but the results will sort of apply. So just imagine there is a tiny loop of wire and there is a current flowing through that. So this will create a magnetic field, and that magnetic field will have a direction something like this. Okay. So if the current is say A, and there is a current is in ampere, but its symbol is I, and the area is A, then you know that the mu as a vector is I times A as a vector. Now, what is this vector A? Oriented vector. Okay, it will be easier for me to draw if the current were oriented in the opposite way. I'll put the current this way, then it will be easier for me to draw. If you have your fingers this way and your thumb this way, the fingers are curled in the direction of the current, and then this will be the direction of the mu vector. It is the right hand Cosgrove rule. So this is the vector A is the vector direction as given by the right hand rule, and this way we obtain the vector mu, the magnetic dipole moment. So this is the magnetic dipole moment. This is rather simple. And if such a thing, a tiny magnet, is placed in a magnetic field, then it feels a torque that tries to rotate it and place it in the direction of the magnetic field, orient it in the direction of the magnetic field. And the torque, again I'll put them as vector, is the magnetic dipole moment vector cross the magnetic field that is applied. So, and this will try to orient it in the magnetic field direction. This can also be looked at in the sense of the potential energy. That means if such a tiny magnet is placed in a magnetic field that's not oriented in the same direction, then it has a potential energy, and that potential energy is I'll say E mag is actually the dot product minus, okay. And if you then consider like any potential energy, the potential energy will that will allow the dipole to be oriented in the direction. That means as these two gets oriented in the same direction, the potential energy reduces, and at the situation where they are in the same direction, the potential energy is zero. So essentially, it's going from the higher potential to a lower potential. Orienting along the magnetic field is energetically favorable. Good. But if you have such a thing placed in a magnetic field, suppose there is a magnetic field, it tries to orient itself in the direction of the magnetic field, that's fine, but it does not feel any net force. That sort of tries to displace the tiny magnet. So the net force will, in this case, will be zero. But if such a tiny magnet is placed in non-uniform magnetic field, so if it is in a non-uniform magnetic field, then it will feel a force, and the force will be suppose I am talking about the force in the z direction. The force in the z direction will be as the behavior of all potentials are. It is the gradient of the potential, the negative gradient of the potential in that direction. So it is minus delta E mag divided by or its derivative with respect to z. Now you know what E mag is. So it is essentially, there are two minuses, and so it will become plus. It is magnitude is mu delta E z, right? Delta z. So it will feel a force. If there is a magnetic field gradient in the direction of z, then it will feel a non-zero force, which will sort of physically move the tiny magnet. Okay. Now,
Sir, that would be BZ.
well,
Sir, in the last expression.
the last expression, yeah. So you say D is a DZ. Why? Because it is dependent on three different directions. I'm only talking about the Z direction. That means I am asking how much will be the force felt in the Z direction. It will be the derivative of the magnetic field in that particular direction. If I ask the question, how much will be the force in the X direction, it will be derivative of the potential along the X direction, and so on and so forth. Presently, I'm asking the question as regards to Z direction. So,
No, sir, you have written mu delta Ez del Z. So it will be BZ because in the expression of E we have mu B.
oh, sorry. Oh, I was understanding it wrongly. Yes, BZ. You are right. Yeah. Yes, I just put that in. Yeah. So now, therefore, if you have a gradient in the magnetic field in the z direction, the particle will feel a force in the z direction. Uh, Now, if you consider a situation where there is a particle moving in a loop, a charge particle moving in a loop, charge particle moving in a loop like this, and the charge particle, say here, is having a charge q, uh, then with speed v, then it will, its angular momentum L, we know is mvr. That's something that you learned in school. And what is the current? Current is essentially charge passing per unit time. If you consider a particular point here like this, the charge that is passing per unit time, that is the definition of current. So it is q, and how much charge is passing is q, and the length of the path is twice pi r, and the velocity is v, and so this will be divided by twice pi r by v. So this will give you q v by twice pi r, right? So that will be the current. And we have already seen the mu, the magnetic dipole moment, is I cross A. Therefore, it is in magnitude qv by 2 pi r, that is the current, times the area pi r square, that is equal to, it will be half, pi cancels off, r cancels off, it is qvr. So it is, I need some space, let me finish this here and then go. And this means I'm not considered this as a vector. This can be, the q can be positive or negative. So ultimately, let me talk about the magnitude. The magnitude of mu is half the magnitude of q. Q could be positive or negative, v r. So the magnetic dipole moment has a specific value. Now notice it is very classical picture because I have drawn a specific orbit of the charge. In quantum mechanics, you cannot define such an orbit, but nevertheless, we are presently trying to explain it in terms of the classical mechanics. So the angular momentum is then, we have seen that this mvr, that's equal to, here is vr, so we can put it as the mu as a vector is, mu as a vector will be q, q as a q magnitude by twice m, and it will be the L. So so we are essentially using this. So there is a relationship between the L, which is the angular momentum, and the magnetic dipole moment. These two are related to each other by a coefficient. Now this coefficient need not be the same for quantum mechanics as we have found in the classical picture. The classical picture is related very much to the existence of an orbit and things like that. But this will then be in general, we can write that this is gamma times L. This coefficient is really true in quantum mechanics also. So this is called the gyromagnetic ratio. It will not exactly be q by twice m, but it will be at least a coefficient, which means that the fact that we have derived, the argument that we have given is that the mu vector, the magnetic dipole moment, is proportional to the angular momentum, or in other words, the angular moment is proportional to the dipole moment. Then, uh, then if we can have some way of measuring the magnetic dipole moment, then we also get some way of measuring uh, the angular momentum. If we can find in some way that this is quantized, then L also becomes quantized. If we find that this can take discrete values, this also takes discrete values. That's the logic. Okay. So on that basis, Stern and Gerlach set up the experiment. I'll go into that now. So notice that this will depend on setting up a non-uniform magnetic field. So it will require a non-uniform magnetic field and the passage of a particle through a non-uniform magnetic field. Okay, so here it is, the arrangement of the Stern-Gerlach experiment. Here you have a oven where silver is heated, solid silver, but if it is heated, it becomes vapor. So silver vapor is generated here, and in this box there is a hole, tiny hole. Through that, the silver atoms come out, and these atoms, or the beam of the atoms, is collimated into a narrow pencil-like beam which shoots through in this direction. Now here you have a magnet, but since the the particles are not charged, uncharged particles, silver atoms are uncharged, then it will not normally be deflected. But uh, Stern and Gerlach deliberately created a non-uniform magnetic field by making the pole faces like this. One with a pointy concave convex surface, the another is a concave surface. If you look at here, you will see that this is a convex surface, this is a concave surface. As a result of that, uh, the the direction of the magnetic field lines will be like this, and it is clear that there will be larger magnetic strength in this part and a smaller magnetic field strength in this part. So B larger here, B smaller here. So there is a gradient of B in this direction. Now uh, that non-uniformity of the magnetic field, as we have seen, will make the reflect if there is any angular momentum carried by the particles. So it is dependent on the angular momentum, the deflection. Now, what do you expect? The angular momentum of the particles, since these are generated in an oven with no specific orientation, they will be oriented in any possible way, which means that there will be some atoms oriented in this can be called the z direction, in the z direction. There will be some which will be in the minus z direction. There will be some which will be in all possible directions. So their components in the z direction can have any value. As a result of that, what you expect is that there will be a collection of points. This will be spreading in this direction. It will spread in this direction because some will be deflected in the upward direction, some will be deflected in the downward direction. There will be a collection of dots then. So that is what we expect. Let me draw it here. So like this. Okay. So the ones that have the largest deviation will go there. But what they actually saw was that there are only two dots. So this is expected. And what they actually saw was that there are only two dots. So this is actual observed. So this is somewhat unexpected. It is expected that if they contain some orientation of the angular momentum, that orientation could be any possible orientation, and therefore there should be all possible components along the z direction, and therefore they are expected to deviate by various possible amounts, but they're actually found to be deviating by a specific amount, which means that the angular momentum in the z direction is quantized. This is what is the prime conclusion of this experiment. We expect something like this: many atoms to fall and the distribution to be something like this. What was actually observed in this Stern-Gerlach experiment was that there are only two spots. There are only two spots. To be accurate, the only two spots situation is actually obtained in modern experiments, because when you are allowing the atoms to go in a narrow beam, it is not absolutely narrow. It has some spread in the x direction as well, as a result of which there will be different spreads in this direction, and moreover the speed of the atoms will be different, and therefore different atoms will be disturbed in different ways along the z direction. So effectively what they saw was a spread something like this. The ones that are somewhat away in the x direction will not feel as much, or I would say that the ones that are somewhat away from the center in the x direction will not feel as much gradient in B, so they will be deflected less, but in the middle they will be deflected more. So this is what the kind of result that we obtained. But modern experiments have been done where the speeds, the velocities of the atoms are also sort of regulated, and there you find truly proper two dots. Okay. So effectively the experiment resulted in the fact that there will be two dots, not a smudge of dots along a line. This was completely counterintuitive, because any logical argument will show that the atoms can be oriented any which way, and as a result they should be spread out in a continuous smudge of dots. The maxima will be given by those atoms that will be exactly oriented in the upward direction or the downward direction, but that does not happen, which means the magnetic dipole moment has two values. It is not having various values in the z direction. It just has two values. And if the magnetic dipole moment has two values, then obviously the angular momentum also has two values in the z direction. Now this was a completely counterintuitive result, and we now have the task of explaining by using the postulates of quantum mechanics. So let us try to explain it. And in order to explain this, that means the quantization of angular momentum, we start by recapitulating the expression of the angular momentum. Angular momentum was L. If there is a there is a body here, r vector, and say this is moving in a particular direction, say like p vector. So it is just r cross p. And this is equal to the basis vectors ex, ey, ez, and this will be x, y, z, x, y, z. This is what you learned earlier about the character of the angular momentum. So if you want to calculate that, it will be ex times eypz minus pyz. So this kind of permutations will be there. So you can say if we express this as L as a vector is equal to something, the component along the x direction times ex plus a component along the y direction times ey plus a component along the z direction times ez. Then you can see that our here our Lx is equal to y pz minus z py. So Ly is zpx minus xpz, and Lz is xpy minus ypx. Okay, so this is what we needed to recapitulate in terms of what you knew earlier, and then on that basis, let us go ahead. What we'll do essentially is that what we have done in the earlier studies in quantum mechanics also, whenever we want to express something or something that was an observable, I want to obtain the equivalent operator, then we used to write down the expression for the observable in the classical terms, the expression, and then in place of those operators, we'll simply replace the equivalent operators. That's what we did. For example, the Hamiltonian operator has p square by twice m. We put minus ih cross del del x. In place of vx, we put the expression for the potential operator, so on and so forth. So in each of the position, we'll replace it by its equivalent operator. So we know already that that px as an operator is minus ih cross del. We know py is minus ih cross del del y, and pz is minus ih cross del del z. We know that. And so we can substitute these guys here to obtain expressions for the operators Lx, Ly, and Lz. So we'll do that quickly. We'll just delete and get some space, otherwise it'll be difficult. So if you now express, I will presently need only the Lz part, so I'll not write the other parts. We'll just write the Lz, which was xpy, sorry, py minus ypx. If you want to convert that into the operator, these will be operators. These will be operators. So we know x is just multiplication by x. So and this will be just what I wrote in the last class, blackboard. So it minus ih cross will come out. It is then x that's multiplication by x, and this is del y minus y del x. Okay. Presently, I'll not bother about the Lx and Ly. You can easily express in similar forms. Okay, because I said that I'll go through this part a little faster than usual. Now, whenever you have things like this, in many cases, it becomes convenient or simpler if you express it in a different coordinate system. So in this case, it will turn out that it will be easier to write in a spherical coordinate system. So in the spherical coordinate system, if I draw the spherical coordinate system quickly, these were the rectangular coordinate system, and I have a vector like this. So I will put an arrow so that you know that this is the vector I'm talking about. And then I will get a, here is a vector, and there will be another component of this. Okay. So now we have the angles, like this is the, sorry, this angle is my theta, this angle is phi, and this is our r. This distance is r. So we can see that easily we can work this out. Your x coordinate, so this is my x, this is our y, and this is our z. So x coordinate is r sine theta cos phi, y is r sine theta sine phi, and z is just r cos theta. Okay, so therefore we can express the rectangular coordinates in terms of the polar coordinates. And if we do that, again, I'm going a little faster, and I just claim that Lz in the polar coordinate can be expressed very simply as, sorry, it will be an operator. Only this much. Still, I'm uncomfortable about you having to accept that, though you might have learned this earlier. You can quickly check by actually applying del f, del phi on this one you apply on some arbitrary function f. This can be expanded as del f, del x, del x, del phi, plus del f, del y, del y, del phi, plus del f, del z, del z, del phi, and then you can substitute these ones from here, and you will find that that yields exactly what you started with here. So this is something I leave it to you so that you can do what you wanted to do. Well, at this stage, do you have any question up to this point? Because it is already about 40 minutes, and I'll take another 15 minutes to finish, maybe even less. Let me then just delete this and continue with this one. You might need drawing it again will be boring. No question at this stage? Well, let's go ahead. So we have obtained that Lz is minus IH cross del phi. Now let us operate Lz So operate LZ on any psi. Now this I will now express in terms of r theta phi, because we are now in this coordinate system. So and let this be an eigenfunction. So then obviously if you operate this LZ on r theta phi, then you will get some eigenvalue times psi r theta phi. So this is nothing but minus I h cross del phi of psi r theta phi is equal to alpha psi r theta. Okay. Now here is an operator. Here is an operator which depends only on phi. Therefore, the psi function will have two components. One component will depend on phi. The other component will depend on, or other component will not depend on phi. So we can write for the sake of simplicity, psi r theta phi as, so we are assuming this is some function of r theta, another function of phi. If we put it here, then we get minus I h cross del phi of g r theta f phi is equal to alpha g r theta f phi. And it is clear that this will come out because it does not depend on theta, and this will cancel off, so I can easily directly cancel this. So we have an equation minus I h cross del phi of f phi is equal to alpha f phi, or what I'll do is I will get this one this side. It will become if I delete this from here, it will become minus I h cross. So I can simplify this by saying I upstairs. All right. So this is a first order simple equation whose solution is easy to write, something that you know. F phi is equal to some coefficient, some constant a times e to the power alpha I alpha is in terms of phi by h. Okay. Good. So we have obtained a solution in this direction. Let us simplify further, because I do not need to keep all these terms. We can say a e to the power I m phi, where I'm saying that m is equal to here is alpha, this is cross alpha y. Well, now this function has to be continuous, has to be finite, has to be normalizable, and all that. So the most simple requirement is that as you go around the z-axis, that means phi goes from 0 to 2 pi. As you go around the z-axis, phi goes from 0 to 2 pi, it will join up to the same value. It is a function that depends on phi, and it should be a continuous function. Therefore, at 0 and at 2 pi, it should have the same value. So that immediately implies, I'll delete it here and I'll write it. Give it the space I need. So what we actually conclude is that a e to the power, it is I m phi. So I m phi plus 2 pi, I m phi plus 2 pi should be equal to a e to the power I m phi, right? Because it has to join up, it has to have the same value as it goes around 2 pi, and this immediately implies that e to the power I twice m pi is equal to 1. And this immediately implies that m can have only discrete values. So m can have values, well, 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4, and all that are allowed. So it is basically, you can say 0, plus 1, plus 2, and here minus 1, minus 2. All these values are possible, but nothing intermediate. Only these values are then possible. Now that immediately results in a quantization, because you would notice that your phi is the solution. Your if phi is the solution, and what you can actually observe are the alphas, because we had operated the L operator on the phi function, and its eigenvalues were alpha, and alpha is m h cross. And since the eigenvalues are m h cross and m can have only these values, the actual observable values of the angular momentum becomes discretized, becomes the actual observable values of LZ, sorry, of LZ should be minus 2, m can have these values, minus 2 h cross, minus h cross, 0, h cross, 2 h cross, and so on and so forth. Only these values. So we have succeeded in proving that the z component of the angular momentum should be discretized and should have these values. So the moment we did it in the quantum mechanical domain, this conclusion comes as a immediate result, and we are happy. We have now obtained the values. The only additional thing I'll do today is that what should be your coefficient A? The coefficient A should be such that the function actually becomes normalizable. So effectively what we need is the f, sorry, it is the f of phi should be, it was actually a e to the power I m phi. M is discretized. What should be the a? That's what you're asking. It should be such that that the whole thing is normalizable. I will claim first, and then we'll go. I'll claim that this has to be root over 2 pi e to the power I m phi. It's easy to check because all you need to do is to check that it integrates from 0 to 2 pi f phi square d phi. Then it should be if this is substituted here, it is 1 by 2 pi, and it is integral minus integral 0 to 2 pi, 0 to 2 pi. It is e to the power I m phi square d phi. This will actually become 1. So this is equal to 1 by 2 pi. And this, when evaluated from 0 to 2 pi, will give 2 pi. So only if you take the coefficient as 1 by 2 pi, then only you get this function to be normalized. And that's why we have taken this as the coefficient. So what we have achieved today, I'll stop here. What we have achieved today is that we have obtained the f function. It was actually the actual eigenfunction was broken up into two parts. One part was g, that's not dependent on phi. Another part was f, that is dependent on phi. And that part has this expression. That's what we obtained. And we have obtained the very important result that the angular momentum in the z direction will be discretized, will have discrete values like minus 2 h cross, minus h cross, 0, plus h cross, plus 2 h cross, and so on. So, and the coefficient that we have obtained.